Okay, lads and ladies, good morning. Welcome back to Calc 2. Today we're going to continue where we left off last time. So last time you may recall, I'm sure you recall, hopefully you recall, we were working on integration by parts. And we solved a nice, big family of problems like that, like integrating any polynomial times any exponential, sine or cosine, integrating the natural log or functions involving logarithms, integrating the inverse tangent function or other functions defined to be inverses of some other better known function. Today, we are going to attack kind of the last family of problems that are native to integration by parts land. And then we will, there's a very nice segue from that into our next section, which is section 7.2. Now, really quick, a few things. I noticed this morning that there were a handful of extension requests that came in on Friday that I did not grant Friday before I finished for the day. So apologies if you submitted an extension request last Friday. It has been granted. Sorry you had to wait over the weekend. I'll try to watch those a little more carefully in the future. The other thing is that homework 3, the homework set from last week, I did extend through to this Wednesday. We talked about that in class on Friday of last week, because that did have one looping integral in it, I believe. And that looping integral is something I'm going to show you how to do today. So we talked about finishing all the other IBP stuff, saving the looping integral for today. And so in order to give you time to do that, I've extended that homework set until Wednesday. So if you haven't finished homework 3, don't panic. You have until Wednesday to do that before you need to file any extension requests. And then today we are going to see how to solve those last few types of problems. So this is MAC2312, section number 004, which is Calc 2. And the date today is the 24th of January, 2022. And as promised, today we finish integration by parts, which was section 7.1, by talking about looping integrals or looping IBP. And then we're also going to begin the section on trig integrals. Which is section 7.2. And I'll talk about this when we get to it, but I know that among Calc 2 students, there is a certain allergy to trigonometry. It's not unique to Calc 2 students, of course, right? Calc 1 students are deeply allergic to trigonometry, and pre-calculus and trigonometry students themselves are allergic to trigonometry. But this is the place where it catches up with you. So I know that the fraction of especially test problems in Calc 1 that involve trig functions is somewhat small. In this class, we're going to do a shitload of trig. So section 7.2 is obviously all trig. And section 7.3, the one which follows it, immediately takes integrals that don't have trig in them, and we solve them by turning them into trig integrals. So for the next few sections, we will be writing the trig hard. So you may want to build a little bit of time in to study your unit circle, to remind yourselves the trig identities, to remember how to draw right triangles and solve for one side in terms of the others, those sort of things. Just a little warning, we will do lots of trig. But before we get there, I want to come back to section 7.1 and talk about those problems that we didn't get to talk about last week. I did not want to rush you through that. So I'm actually going to begin by talking about this concept from physics. Which it's a fun sounding thing. It's called the damped harmonic oscillator. And if you want to sound intimidating at a dinner party with your other academic friends, you can say, oh, I want to talk about the damped harmonic oscillator. It sounds very nerdy. It is what it sounds like if you think about the words one at a time, assuming you understand what a harmonic oscillator is. So if you take a spring if you take a spring and you attach a mass to it and you pull that thing down, assuming there's nothing else going on, no friction. Oh, this has a driving force. We don't want a driving force. You will get what's called a harmonic oscillator. Here you go, simple harmonic oscillation. Right? This is a spring, it's attached to the ceiling here. There's a mass on the end. I pull it down and I let it go. It goes meow, 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 meow. And assuming no energy is lost to heat, which of course would happen in the spring, then what you will get out of this, if you imagine a graph going by, is a sine wave or a cosine wave. Let's see if we can have one that generates. Here it is. Right? Just measuring the height of that thing, the displacement from its equilibrium, and letting time go by, you get this sine wave. Now, separate from this, I want you to think about leaving a convenience store. I know this is a weird change, but leaving a convenience store or walking out of a door at any kind of large commercial institution, even the college. If you look at the top of those doors, they have these little arms that are attached to like a little metal box that's mounted to the top of the door. That's called a dash pot. Right? This thing. This thing. It's called a dash pot. And what's going on in there is that there's a little cylinder that's filled with some fluid, and there's a little piston that moves through that fluid, and the fluid slows or dampens the movement of that piston. This keeps you from being able to slam the door. If you ever try to slam a door that has one of these things on it, it'll go and it'll very gently close no matter how angry you are or how big a point you're trying to make by slamming the door. But what I want to talk about is what happens when you combine those two things. So you take a dash pot, which dampens the motion of a harmonic oscillator. What you get Right, so here's my normal mass, and if I pull this down and let go, it'll oscillate up and down and generate a regular sine or cosine wave. If I attach to this a dash pot, if I have a little arm here that connects the thing to a dash pot, then when I pull the thing down and let it go, it'll still oscillate, but because that dash pot dampens or softens, restricts the motion of the oscillator, it'll go bow, 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 and it'll bounce less and less each time, right? Like imagine putting a shock absorber on the thing. That's effectively what we're doing. What this generates, if you think about the motion over time, so if I call this my y-axis, right? And I call the height of this, the position of this mass y of t, then as this oscillates up and down, the dash pot is going to make it oscillate less each time. So you're going to get a curve that looks like a sine wave or a cosine wave, but the amplitude is like decaying really quickly. And the standard way to describe such a thing is like this. So the e to the negative at, that's your dampening effect. This is a function that goes to zero very quickly. It's an always positive function that decays to zero very quickly. And then cosine bt, that's your normal oscillator. That's your normal wave. The frequency of the oscillation comes from the number b, and the rate of decay, or how strong the action of the dash pot is, slowing things down, that comes from the constant a. I can show you a particular example in Desmos very quickly. Why am I not getting my, I'm gonna use this. Maybe that's too small. Yeah, okay. So what you see is a cosine wave whose amplitude is decaying very quickly, right? This is your damped harmonic oscillator. It starts out swinging back and forth from here to here, and then it swings less and less and less each time. If you look at just the exponential, negative 0.1x, there he is, right? And you see that it's this piece, the blue piece, that's causing the thing to decay. That's the action of the dash pot. And if you were to omit that and just look at the cosine, it would be a regular cosine wave with amplitude 1. These show up in a lot of important places in physics. They'll show up in problems like this. You will see problems like this if you take a good physics or differential equations class. But the more classic example is if you had a planet that's, or like a satellite that's orbiting a planet, but it's not orbiting fast enough, so it starts to fall in towards the planet. If you look at such a system straight on from the side, right? So like here's my satellite going around the planet, my planet's right here. If you look at that just from the side, it looks like the satellite just goes back and forth, right? And if the thing is in a stable orbit, it'll just look like it's going back and forth all the time, same amplitude, same frequency. But if the satellite is spiraling into the planet, and it's going to eventually crash, then this is going to look like it goes back and forth, but a little less each time. That's a damped harmonic oscillator, just looking in from the side. So very important examples in physics, and you need to know how to integrate functions like this. So in physics and engineering, we sometimes need to integrate functions like these. And this requires a special kind of integration by parts, right? If I asked you to integrate this with respect to the variable t, right, and I'll do it with x's just to make everything as nice as possible, then you do see that this is like one function times another function. So it is the sort of thing that your brain should jump to integration by parts right away with. But the trick is that it doesn't come out like a normal integration by parts problem where you run integration by parts and the hard part like goes away and then you do the easy integral that's left over. It's not like that. These require looping IBP. And by looping, what I mean is after some work, the original integral shows up. That's what looping means. So you're going to do some integration by parts, and then instead of the answer to the problem dropping out, the original problem shows back up. And that gives you a way of solving for the original integral. In fact, solving an algebra relationship for the original integral. And we outlined that procedure just a tiny bit at the end of class on Friday, so I won't go back through that. All right, but this is the motivation. There are many, many systems in the real world which are damped harmonic oscillators. And if you want to find the displacement in the physics 1 sense, or the distance traveled, that sort of thing, then you need to integrate a function like this. There are settings in electromagnetism where these are very important also. Okay, so let me remind you the integration by parts formula. Integration by parts says the integral of u dv is equal to uv minus the integral of v du. This is the formula we will use. And we want to apply that to the integral of like e to the negative at cos bt. I'll look at a particular example, but just want to get all the recap stuff here in one place. Any questions about the kind of intro or recap? What we need to remember, what we're doing, sort of thing? Okay, then here we go. So for my example, I'm going to do just e to the negative x cosine of x. Keep it as simple as possible. So here a would be 1 and b is also 1. We're going to run integration by parts, and I can use my LIPET rule to choose u and dv. Right, that will work here. So do I have any logarithms in this? No. Do I have any inverse functions in this? No. Do I have any polynomial functions in this? No. Do I have any exponential functions in this? Yes, I do. Yes, I do. E to the negative x is an exponential. So that's what I'll choose for u. And then everything else is going to be dv. So dv is cosine of x dx. I need to calculate both du from u and v from dv. To take the derivative of e to the negative x or e to the negative 2x or anything like that, you need the chain rule. Remember how the chain rule works here? The exponential is the outer function, and then the negative x or negative 2x or whatever is the inner function. So this would be e to the negative x times the derivative of negative x, which is negative 1. So that's negative e to the negative x dx. That's a chain rule derivative. I'm just putting the negative out front, right? Derivative of e to some stuff is e to that stuff times the derivative of that stuff. And then the antiderivative for cosine is sine. Oh, yes, sorry, give me just 1 second, gang. All right, we're back. So according to my LIPET rule, u is the exponential, dv is everything else, and this is how the IBP table completes. All right. So now I just apply my integration by parts formula. It says, I'm going to write the whole thing here. I'm going to write the original integral of e to the negative x cos x dx is equal to u times v, so that's e to the negative x times the sine of x minus the integral of v times du. So that's sine of x times negative e to the negative x dx. Okay, and just a comment on notation, the parentheses around the e to the negative x, that's necessary because otherwise this would look like subtraction, right? So just, use good notation, use clear symbols to represent what you're doing. Here's the result doing integration by parts once. I'm just going to simplify this right-hand side. This piece is just chilling, he's done. This piece, I can, when I multiply sine x and negative e to the negative x, I get negative e to the negative x times sine x. And the negative is a constant multiple that can come out, and that'll make this a plus. All right. And now I look at this integral and ask, have things gotten better? What should I do with this? I would say things have gotten neither better nor worse, right? It's identical to my original problem. It's just that the cosine has been changed into a sine. And that hints at something. That hints that if I were to do this again, run another integration by parts, I would get some more shit looking kind of like this, and then another integral where the sign will have changed back to a cosine. In other words, I'll have looped my integral. I'll have gotten my original integral back again. And that's what we want. So we're going to run another IBP. Second run of integration by parts. And I'm going to choose u and dv the same way. U will be e to the negative x again, right? I'm doing it on this integral right here. And dv is then forced to be everything else, which is sine x dx. Du, the derivative of e to the negative x, is still negative e to the negative x dx. V, the antiderivative of sine x, is negative cos x. So be mindful of your negative signs. And we want to be very disciplined in how we write things. So I'm going to continue writing the e to the negative x sine x piece here. I'm not doing anything with him in this stage, but he comes along for the ride because he's a part of the line that we had up here. And then plus, and now this integral I am replacing by his integration by parts equivalent. So that's u times v. That's e to the negative x times negative cos x. And then we have minus the integral of v times du. And that's negative cos x times negative e to the negative x. Dx. And I can simplify a little bit. We have e to the negative x times the sine of x. These terms here, this is minus e to the negative x times the cosine of x. And then you have 1, 2, 3 negatives here, right? So negative cos x times negative e to the negative x, that would be positive. And then you've got a negative coming from the IBP formula, so this will stay negative. And let's rewrite it as e to the negative x times cosine of x dx, because it looks fine. And the magic thing has happened. The magic thing is that the integral you get down here after 2 runs of integration by parts is identical to the integral with which we began. So my original integral is equal to this, which is equal to this, which is equal to this, which is equal to this. This is why this notation of chaining equal signs together is important. It's not a nothing thing. If you call this integral I, then what we've shown here is that I, my original integral, is equal to e to the negative x sine x minus e to the negative x cos x minus I. Right, this is also I. I'm using I here for integral, right? The integral I want. And this is an algebra equation that you can solve for I. No more calculus. We did all the calculus. If I want to know what is I, from this equation, you can just add I to both sides. When you add I to both sides, over here you'll have I plus I, which is 2I. And over here, this is the I we're adding over. So you just get e to the negative x sine of x minus e to the negative x cos of x. Divide by 2. Or multiply by 1/2. So you add this guy over here, and that gives you 2 times your integral equals some stuff. Well, that means that your integral equals that stuff, i.e., the integral of e to the negative x cos x dx is equal to this expression. And we need to write a plus c here technically. All right, indefinite integral, so I'll add my plus c here. But this is that thing that last week I said is, kind of brain melty the first few times you see it, because it's like, when did I solve the integral exactly? At what point did I find the antiderivative for e to the negative x cos x? Well, we didn't do it directly. We do it very indirectly by using integration by parts to come up with this equation that we can then solve using algebra for the antiderivative we're looking for. It's very clever. So you may remember me saying integration by parts is one of the most important theoretical methods known to mathematics. Legit research attack is just try integration by parts, even at the graduate level. Here we go, right? This is the sort of reason for that stuff. So I'd like you to take a second and just look over your notes and make sure you have all the steps, because that being able to review a nice clear solution is an example is always important. So make sure that your notes are nicely organized. If there's anything you want to insert or any questions you have, now is a great time to ask them. Okay, I have one little comment for you if there are no questions. Are there any questions, Liz?
I have a question. Why did you do 2i on the left?
So here in this equation, I'm going to add I to both sides. Think of it like baby algebra class, where you just, I'm solving an equation like x equals 7 minus x. You'd add x to both sides and get 2x equals 7, right? Same sort of thing. So when I add I to both sides in this line, here I have minus I plus I, the I goes away. And over here I have I plus I, which is 2I. So we treat this like an algebra equation, like a 7th grade algebra equation, which is bizarre. I would like to show you one more example where the constants are not quite this clean, and that might help see the two, but did that particular answer help you feel more comfy with this guy?
Yes, thank you.
Sweet. Okay. Other questions or comments on this one? Do we all see where this equation came from? think that can be a little bit tricky. So here's I, and then equals e to the negative sine x minus e to the negative x cos x minus I. So I'm taking my very, very starting thing here. This is I, and then setting it equal to this, where this is also I. And that's the magic of getting your integral to show back up. Then if you're lucky, as long as there's nothing else going on, you can just straight up solve the algebra equation for your integral. Correct, Tyler. Yeah, if we have a problem that we know we should attack as a looping integral, we want to work with integration by parts, or perhaps some trig identities, whatever tools we have, until our original integral shows back up. And that is the looping. You have successfully looped the problem when you get your original integral I to show back up. Yeah. Or it could be 2I, or negative 0.3I. Any constant multiple of your original integral, we could then write down an equation like this and solve. Yes, Mark makes a good, oh, it's a DM, so you guys can't see it. So am I fibbing a little bit in one of these steps? Yeah, here, if we're being very picky, then I should have a plus C here and a plus C here. If we're being picky, this line is okay, because there's an indefinite integral here. I is an indefinite integral, and there's an indefinite integral here. But at this line, where on the left-hand side, I have an integral, but on the right-hand side, I have no integral, that's technically the line where we should start writing plus C. I didn't want to give you any more than you needed to solve the problem at that moment, but it is true that if we want to make sure everything we write down is 100% accurate and correct, then this is the line where we should begin writing our plus C's. But as long as you remember to tuck it in at the end, I won't take off from you on the test. I don't want you to have more things on your plate than you need. But yes, that's correct. Without the green, those lines are little lies. Little lies. Has anybody ever told you guys the credo of the mathematician, or particularly the math teacher? Tell the truth, tell nothing but the truth, but for the love of God, don't tell the whole truth. It's a little silly. Correct. Okay, let me try one more of these. And you'll see how with some other constants in here, things can get somewhat sneaky. So let's do e to the x sine of 3x dx. Same flavor here. Instead of an e to the negative x, I have an e to the x. Well, okay, that doesn't change derivatives much. So it's not going to change anything that we did there very much. Instead of a cosine of x, I have the sine of 3x. Okay, so this 3 is going to mean like some other constants show up as we do our IBP. And also it's a sine instead of a cosine, so the negatives might be a little bit different. And this is the same thing, but requires slightly more care. Slightly more care. But as before, we're going to run integration by parts. As before, you can use your Lipet rule to choose u and dv. So u be e to the x. dv here would be the sine of 3x dx. du is e to the x dx. To integrate the sine of 3x requires a little micro u sub or little micro z sub, and this is something we should be quick with now. What is an antiderivative for the sine of 3x? You can type or you can shout out. Very good. Negative cosine of 3x over 3, or negative 1/3 cosine of 3x. Does everybody see where that's coming from? This is one of those things that I've called a micro U sub. If you're integrating sine 3x dx, I'll do it with z, you let z be 3x. dz is 3 dx, which means 1/3 dz is dx. So this becomes integral sine of z times 1/3 dz. The 1/3 pops out. An antiderivative for sine of z is negative cosine of z. You write your plus c. So this would be negative 1/3 cosine of, and then going back, z is 3x. So these little micro u subs, you want to be able to do these in your head. All right, the passage from here to here, by the time the test rolls around, should not require writing this out. If from time to time you do need to write this out to just check your work or make sure that things are going smoothly, that's okay. But we do want to be able to integrate things like the sine of 3x or the cosine of 2x in our, without writing out all these steps. But those are the steps, if you want them. If you're working a problem, you need this, just do it off to the side. Tuck it out of your workflow like I did. That way things don't get overly complicated here. Here's our first run of integration by parts. I'll get integral e to the x sine 3x dx equals u times v. I'm going to write this as negative e to the x over 3 times the cosine of 3x. So combine the negative 1/3 and the e to the x. Nice like that. And then you have minus the integral of v times du. Again, negative, so I'll write this as, I will just write it like that. Negative 1/3 cos 3x e to the x dx. In this integral, I can do some cleaning up. This negative can come out and combine with this negative to make a plus. This 1/3 can come out. And I can also write the e to the x in front of the cosine to kind of just make it look a little more like this. So that would be my next line, just cleaning up. This is negative e to the x over 3 times the cosine of 3x plus 1/3 integral e to the x cosine of 3x dx. We haven't looped yet, but I recognize this as being very similar to my original integral. If I run IBP one more time to turn that cosine back into a sine, then I will get my original integral. But you need to be very careful with this constant. So I'll set up the second IBP. It's very important that you choose u and dv the same way in both runs of integration by parts. If I were to switch here to calling u cosine of 3x, then I would undo what I just did. So u here needs to be the exponential again. Just follow your Lipet rule, you'll be okay. dv is everything else, cos 3x dx. du is e to the x dx, because e to the x is its own derivative. And v, this time I will not write the steps for the micro u sub. Antiderivative for cos 3x is 1/3 sine of 3x. So that's what this integral is going to be replaced by, the IBP stuff from this second table here. And the 1/3 that's multiplying this integral needs to multiply all the IVP stuff. So my whole line above is equal to negative e to the x over 3 cos 3x plus 1/3 times open a big parentheses. We talked about this a little bit last week. Right? When you're going to replace an integral with its IVP stuff, if there's a negative out here or a constant out here, you need to open up a big parentheses and make sure that that negative or that constant distributes to everything. Now this integral is equal to u times v. That's e to the x over 3 times sine 3x. Minus the integral of v times du, which is 1/3 sine 3x times e to the x dx. And close that big paren. So this 1/3 here is the 1/3 down here. This guy comes from this guy. And this integral here is equal to all this stuff here, according to my second run of IVP. I'm going to distribute this 1/3 over everything in these parentheses. I'm also going to bring this 1/3 out of the integral. So when I do that, I get negative e to the x over 3 times the cosine of 3x. 1/3 times e to the x over 3 sine 3x is e to the x over 9 times the sine of 3x. And this integral is negative 1/3 e to the x sine 3x. When I multiply that by 1/3, it becomes negative 1/9 integral e to the x sine 3x dx. So if I label this as I, and this as I, then I have I equals this stuff minus 1/9 times I. I'm going to add 1/9 I to both sides. Yeah, so let me write it up. So what we get here, therefore, I equals negative e to the x over 3 cos 3x plus e to the x over 9 sine 3x minus 1/9 I. And if I add 1/9 I to both sides, then I get I plus 1/9 I equals this stuff. Negative e to the x over 3 cos 3x plus e to the x over 9 sine 3x. And if we're being careful, this is the stage where we add the plus c. Now, 1I plus 1/9 I, this is 9 over 9 plus 1 over 9 times I, that's 10/9 I. And so your last step is to solve for I, which you do by dividing both sides by 10/9 or multiplying both sides by 9/10. So if I multiply everything over here by 9/10, what happens? Let's write it. Our integral is equal to 9/10 times -1/3. That's it. The 3's will cancel and you get -3/10 e to the x cos 3x. Here the 9's cancel and you just get +1/10 e to the x sine 3x. And 9/10 times c, where c is an arbitrary constant, is still some new arbitrary constant. You can call it, you can just leave it like this. This is fine. And that's job done. So we got to be a little bit more careful with the constants, that's all. But any integral of this form, e to the ax times sine or cosine of bx, they're all handled in this fashion. None of them are any harder than any others, as long as you are mindful of your negative signs and careful with your constants. Questions on any of these steps? There's the whole thing. Okay, so that's your standard looping integral. The other place looping integrals show up is in section 7.2, and one very, very special case. Before we get to that, I want to just introduce section 7.2. Here, we're going to attack kind of two families of integrals. Powers of sine times powers of cosine, and powers of secant times powers of tangent. Now, these, although it might not seem like it, are all you will ever need to do to integrate in order to handle basically any integral of trig functions, as long as the insides are the same, right? X's or thetas or 2x's or 3 thetas. Pretty much any trig integral can be broken down into sums of integrals that look like these. The one exception is that you might have like cosecants and cotangents here instead of secants and tangents. And the rules are the same if you swap like secant and tangent for cosecant and cotangent. So you saw in your Calc 1 problems that a number of trig integrals are most easily handled just by using the definition of the trig functions, right? Like secant is 1 over cosine or tangent is sine over cosine, and splitting them up, handling them as best you can by rewriting them to look nicer. The integrals we're going to attack here don't necessarily require any new techniques, but they require clever application of U-sub for the most part. And one of these will require looping integration by parts. There's a special case of these that is nasty. Some sort of preliminaries. The basic sine AX and cosine AX integrals. These are those micro U subs again, right? These we should do quickly. We should not have to think about these, or think about them, sure, but we should not have to go off to the side and do much work to crunch these out. You know, the antiderivative for sine is negative cosine. And you know that if you differentiate like sine or cosine of AX, you'll get a factor of A. So when you integrate here, you get a negative 1 over A cosine of AX, and plus C. And for cos of AX, your antiderivative would be 1 over A sine of AX plus C. Those micro U subs should be readily available. We don't want to have to work for them. Two other preliminary integrals. Integral of tangent and integral of secant are necessary. We're going to talk about these. But you'll need to remember those as well. Other things you're going to need for this are some trig identities. So we use identities a lot when working with trig functions, especially in 7.2. There are some families. There are some identities that I'll refer to as the Pythagorean identities. These are sine squared theta plus cos squared theta equals 1, which you can rewrite as, you know, sine squared equals 1 minus cos squared, or cos squared equals 1 minus sine squared. There's the tangent secant version of these, tan squared theta plus 1 equals secant squared theta. And there's the cosecant cotangent version of these, which says 1 plus cotangent squared theta is equal to cosecant squared theta. We won't use that one here in class today, but that's what you need to do the secant tangent stuff if it was cosecant cotangent. So the Pythagorean identities we will use like water. The other family of identities we'll use a lot here. Half angle identities. There's two of these, and if you remember one, you get the other for free. Cos squared theta can be written as 1/2 times quantity 1 plus cos of 2 theta, like so. You may have seen these with like x over 2 here and x here, literally the same thing. You may have seen a version of this where it says 1 plus cos 2x over 2, or maybe even with this square gone, having taken a square root on both sides. This is the form that is useful for us in Calc 2. The one you get for free, if you remember the one above, is sine squared theta. All you have to do is change this plus to a minus. Everything else stays the same. So sine squared theta is 1/2 times 1 minus cos 2 theta. And it's nice that both of these end in cosines rather than sines. That's a good thing. There is a third family of identities that we'll use less often here, but quite a lot in 7.3. So if you're putting trig identities in your notes, the place to put them is here. They're called double angles. sine of 2 theta is 2 sine theta cos theta. And cosine of 2 theta, there's a bunch of ways to write this. I'll just write it as cos squared theta minus sine squared theta. There are 2 other flavors of the cosine one. If you have one of them, you'll be okay. I'll tell you right now, these need to be committed to memory. I won't give them to you on the test. You will need them on the test, so you must know these. The way to remember them is to just practice with them. Use them in solving problems. And every time you use one, before you plug it into the problem, just write it down. Write it down somewhere else on the page there. If you do that every time you need it, then you will remember it forever and ever, amen, as long as you solve the homework problems honestly on your own. Emphasis today is on the first 2 families. Emphasis Friday or Wednesday is on the next one. We need to talk about the integrals of tangent and the integrals of secant. So as a little intro, who remembers how to integrate the tangent function? Standard Calc 1 exercise, standard U-sub problem. Does anybody have an inkling? Something they'd like to share, an idea? Nothing? Okay. We write it as sine over cosine. You integrate tangent by writing it as sine over cosine. Yeah, it came to me in a DM there. That's good. This is one that you're going to end up memorizing, right? Like having the integrals of the 6 trig functions memorized is a standard thing that you'll want. But here's where it comes from. It's not hard. You make a little substitution. At this stage, we sub for the bottom, z equals cos x. And in doing that, dz is negative sine of x dx. So the cosine x downstairs, that's going to be z. Sine x dx is almost dz. It's the negative of dz. So this becomes negative integral 1 over z dz. With that substitution. Which we know is the natural log, negative ln absolute value of z plus c. Plugging back in for z, that's negative ln absolute value of cos x plus c. And then the thing that came in chat was the natural log of secant x, which is correct. How do we square that with this? Is there a way to clean the negative ln of cos x up? There's a rule for logarithms that says a times the ln of b. Yeah, exactly. Thank you, Mark. It came in a DM, so let me share it with everybody else. A multiple outside a log can come inside as a power. It doesn't have to be the natural log. It could be any logarithm here, but I'm writing it with the natural log because that's what we're doing. So this negative out front, that's a negative 1 times ln of cos x I bring that inside, I get the I get the natural log of cosine of x all raised to the negative first power. That is the natural log of the absolute value of 1 over cos x and 1 over cosine x, that's secant x. So at ln, absolute value secant of x is the integral of the tangent function. If you prefer to think of it as the negative ln of cosine, that's fine. This is correct. But because secant and tangent connect to each other all the time, right? The derivative of tangent is secant squared. The derivative of secant is secant tangent. The Pythagorean identity is tan squared plus 1 equals secant squared. Every time you see a secant, there's a tangent nearby and vice versa. So it's nice to think of the integral of tangent x dx as the ln of secant x plus c. So the result here the thing you need to commit to memory, but the integral of tangent x dx is the natural log of secant. Down this way. Just like you have your power rule memorized, just like you have the integrals of sine and cosine memorized, the integral of e to the x memorized, this goes in the box, right? You remember this forever and ever on that. Integral of tangent, natural log of secant. The other one is the integral of secant. It's our other lingering preliminary. This is a very silly integral. And I'll tell you, all the odd powers of secant are weird. Anytime you are integrating an odd power of secant, like secant to the 1, secant to the 3, secant to the 5, you're in for a ride. Did anybody see this in Calc 1? This is another integral that we can do in Calc 1. No, okay. So you know how I'm allowed to multiply by 3 over 3, right? If I want to like have a common denominator to subtract or add two fractions, I can multiply by 3 over 3, or by x squared over x squared if I need to have a common denominator with an x squared. I'm going to do that here, but instead of multiplying by 3 over 3 or x squared over x squared, I'm going to multiply inside my integral, so I still have integral secant x. I'm going to multiply by secant x plus tangent x over secant x plus tangent x. And don't worry, this is not something I would expect you to come up with on your own. It's a weird trick that's used for this integral and only this integral. Yeah, I did get a DM, something to do with secant plus tangent. That's solid memory. Let me get this out of the way. So we multiply by secant plus tangent over secant plus tangent for reasons only God knows. But then we distribute. We multiply, remember this is secant x over 1, right? Secant x as a fraction is secant x over 1. So I multiply the tops with the tops and the bottom with the bottom. Downstairs, 1 times secant plus tangent is just secant plus tangent. Upstairs, I have to distribute, right? Multiply secant times secant and secant times tangent, I get secant squared x, that's secant times secant, plus secant x tangent x. That's the secant times tangent. And then my downstairs is the same. Downstairs is just what it was. Sorry, so secant x plus tangent x dx. And the normal way of thinking, like, is this getting better or is this getting worse? You would say this is getting worse. But I promise we're almost there. If you stare at this integral enough, specifically the relationship between the pieces of the top and the pieces of the bottom, something should start to occur to you. Think about where in Calc 1 you ran into the function secant squared. Where in Calc 1 you ran into secant x tangent x. Those should both ring a bell. Where do we see secant squared show up? Genuinely looking for an answer. You can DM if you feel shy, but I just want to feel out what you guys see. Where have you seen secant squared before? Yeah, that's it exactly. Secant squared is the derivative of tangent. And where have we seen secant tangent before? Secant tangent is, yeah, the derivative of secant. That's it exactly. So the top is the derivative of the bottom. So your boy up here is what you get if you differentiate the stuff down here. In other words, if you substitute for the bottom, similar to what we did in the tangent integral, if you substitute for the bottom, then dz is the derivative of secant, which is secant tangent, or secant x tangent x, plus the derivative of secant is secant squared x, all times dx. And wouldn't you know it, that's exactly what I have up here. It's written in the other order, but this numerator is secant squared plus secant tangent, secant squared plus secant tangent, all times dx. So the whole numerator here is dz. Right? Remember, tops and bottoms of fractions are always secretly in parentheses. So this whole thing right here, this is dz. And the bottom, secant plus tangent, that's z. So what we get is the integral of dz over z, or 1 over z dz, which again is a natural log. And I won't do any fiddling with log rules. The answer we get just plugging in will be fine. So from here, under this substitution, we get the integral of 1 over z. The integral of 1 over z dz is the natural log of the absolute value of z plus a constant. And if you plug in your z, this is the natural log of the absolute value of secant x plus tangent x. On absolute values plus c. And with that, we've done all the preliminary stuff. We're ready to get started. So the final thing I need you to add to your memory banks, but the integral of the secant function is the natural log of the absolute value of secant plus tangent plus a constant. The good news is that now you know the antiderivative or integral of all 6 trig functions: sine, cosine, secant, tangent, cosecant, cotangent. Cosecant and cotangent follow precisely the same rules. They're in your textbook. If you like, there is a I don't have it open yet. There is a place in your book where you can find a table of all the basic known antiderivatives. The most complete one is in section 7.5, page 503. Sine, secant squared, secant, right? All your basic integral formulae are here. And we do want to know all of these, right? Coming into exam 1, if you see any one of these at any point in any problem, you should immediately be able to write down the answer. When my wife took this class, we used some flashcards, right? Because there just wasn't enough practice in the homework for her. I try to give you guys a little more practice. The only ones that I'm not going to beat you up on are the hyperbolic functions. We will talk about these from time to time. Actually, these ones you should know, just sinh and cosh on their own. But the more complicated hyperbolic trig, these down at the bottom can also be written as hyperbolic trig. You don't need that. So make sure you know these. Right? Make sure you know these, including, of course, the new ones from today that we just learned. But those are on that table. All right. So now we're ready to do it. We're ready to actually do it. What I said we're going to do is learn to integrate powers of sine times powers of cosine and powers of secant times powers of tangent. The sine cosine integrals are not bad. It's all identities and u sub. The secant tangent integrals, in most cases, are identities and u sub. In one case, you will need to use looping integration by parts for the secant tangent integrals. But we're going to go gentle at first. I know a lot of that, which we just went over, was stuff that you probably hadn't seen in Calc 1 and required some creativity and stuff, but I'd like to return to our usual level of interactivity. So who can suggest an attack for this problem? Wrong answers are okay, just any thought at all. Ooh. Wow, I got 3 suggestions. One of them is precisely what we're going to do, and the other 2, well, are not what we're going to do. They weren't the bait I was thinking of, so I appreciate those answers. Suggestions were looping, maybe factor out a cosine, or apply a half angle identity. I'll tell you what me being naive would think if I was given this in your position. My first thought would probably be to substitute for cosine, try to turn it into u cubed. And that's a reasonable thought, but it's not the correct one. So I want to make a note here. If we tried to sub z equals cos x to turn this into the integral of z cubed, which would be a pretty natural thing to try, then dz would be negative sine x dx, and I don't have a sine x in my integral. Which is what I would need to make this work. Right? We know we need to convert all the stuff in the original integral into new variable stuff when we do the substitution. If you replace dx by 1 over sine x dz, there's no sine x to cancel here. So this, which is a very reasonable thought, won't work. one of the suggestions I received in chat was to factor out a cosine. So to write cos cubed instead as, come on, good purple pen, where are you? As cos squared x times cos x, and dx still showing. Which is not something most folks would think to try right away, but it is the right move. It's the right move if you want to substitute for sine. Because if I was to substitute z equals sine x, then dz would be cos x dx. So what I'm doing here is I'm setting aside a copy of cosine with the differential, thinking about making the future substitution z equals sine of x. And you might say, why would you substitute for sine of x? The only other thing you have is cos squared. But cos squared is 1 minus sine squared by the first Pythagorean identity. So here is the work we do before the substitution. And I will tell you in a minute how I knew to do this ahead of time. There is a clue in the original integral. This is coming from the fact that sine squared x plus cos squared x is equal to 1. If you're ever uncertain, just go back to that. Solve for cos squared now. Subtracting sine squared from both sides, I get cos squared is equal to 1 minus sine squared. So I've replaced this cos squared with 1 minus sine squared using that identity. From this line, if I gave you the integral in this form, I hope that most of you would see the way to do it is to sub for sine. So now I let z be sine of x. dz is then cos x dx, which is lovely. So I have a cos x sitting over here next to dx. This is dz. This is 1 minus u squared, or 1 minus z squared. And the blue you wouldn't normally write. Normally you would just write the purple. And we're home free now. I know how to integrate 1 minus z squared. That's a polynomial. That's going to be z minus 1/3 z cubed plus a constant, according to the power rule. And then, since it's an indefinite integral, I do have to replace this variable z by what it was originally, which is sine x. So this is sine x minus 1/3 sine of x all cubed, which is sine cubed x plus a constant. That is the integral or antiderivative of cos cubed. Not bad, right? And notice that it's not cos to the 4/4. It's not like you can just apply the power rule here. That doesn't work. Any questions on this? Okay. I want to point out this does fall into the scheme we're talking about, power of sine times power of cosine. The power of sine here is just 0. Our next example, look at the integral of sine cubed x times cos squared x dx. This is similar in spirit. I'm going to solve it with a u sub. But before I do the u sub, I'm going to do some trigonometry to write this as a polynomial in one of the trig functions, like powers of cosine or whatever, times one of the trig functions set aside to help me with my substitution. And the way you decide which one to grab off and set aside is whichever one has the odd power. So I'm going to take the sine here has an odd power. So I'm going to take one of him and set it over there. I'll leave the other two here. So that's sine squared of x times cos squared of x times sine of x dx. So whichever one has an odd power, grab one of those and leave it over here. Everything else now, well, if I've got a sine set over here, that means my goal is to sub for cosine. So I should try to rewrite everything over here as cosines. And I do that by using the fact that sine squared theta, or sine squared x, is 1 minus cos squared x. And what I'm doing is setting up a u sub. This is now a great integral to substitute for cosine in. If I do that, if I sub z equals cos x, dz is negative sine of x dx. So this sine of x dx will be negative dz. And that's all multiplying this stuff, which would be 1 minus z squared in parentheses times z squared. The negative from the dz, I'm going to bring all the way out front because it is a constant multiple. So I get negative integral parentheses 1 minus z squared times z squared times dz. And the negative that was with the dz is now out front. One minus cos squared x, 1 minus z squared. Cos squared x, z squared. Sine x dx is negative dz. Here's the negative, here's the dz. And again, integrating this is now a piece of cake. Polynomial, I love integrating polynomials. I could integrate polynomials all day. I could do it in my sleep. My dog can integrate polynomials. And he's not even a smart dog. Distributing the z squared, I get z squared minus z to the fourth dz. And applying the power rule, I get 1/3 z cubed minus 1/5 z to the 5 plus a constant. And then finally, I distribute the negative and I plug back in for cosine. So this would be negative 1/3 cos cubed x plus 1/5 cos to the 5x plus a constant. And the pattern that you think you're seeing, you are seeing. If you have a sine cosine integral and one of the powers is odd, you're going to do u sub for the other guy. And the way you make that happen is by taking one of the odd powered functions and setting it over here with the differential. That will leave you an even power of that guy, because an odd power minus 1 is an even power, which you can then rewrite using Pythagorean identities, enabling the substitution. Now, I'll pause here for a second. Any questions on this? Comments, crises, concerns? Deep ambivalence? No, there's not a specific name really. It's just u sub. But we're using trig identities along the way, right? So using this trig identity is very nice. I think we are about out of time for today. So I'm going to wrap up by summarizing what we're doing here. There are plenty more of these to talk about. But let me give you the strategy for the sine cosine integrals in general. And next time we'll look at some more of these. If one of the powers is odd, either one or both, set aside a copy of the odd powered function with the dx at the end. Then rewrite the remaining powers of that function in terms of the other function. And this will always be done using Pythagorean identities. Then finally, sub for the other function. This is your general strategy. And this is about as nicely as I can say it without getting annoying and granular. If you look in the textbook, they get annoying and granular. Okay, so there's the odd powered function and the other function. If sine is the odd powered function, you'll set one copy of sine aside with dx, rewrite the remaining powers of sines as cosines using the Pythagorean identities, and then sub for cosine. All right, so I think this is where we have to leave it in order I avoid going way over time. So I am going to stop here. I do have an office hour. Maybe just let me. So in the integral, like cos to the 4x times sine cubed x dx. Long run here, we're going to sub. This will end with the substitution z equals cos x. And in the integral sine to the fifth x times cos squared x, you would set aside one copy of the sine function with dx, and this will end with the substitution z equals cos x again. And we'll do one more just so we have an example of each. If we had something like sine to the 4x times cos to the fifth x dx, you would set aside a copy of cosine with the differential, and this will end with the substitution z equals sine x. All right, so without going through the details run the same sort of way we outline in the strategy there. These are the substitutions that you would use at the end of each of those problems to make them go. We haven't talked about what to do if neither power is odd, right? If both powers are even, you'll do something else, namely work with the half angle identities. If both powers are odd, then it's up to you. It's up to you. You can sub for either one, but if both powers are odd, then you're in this scheme where you would still set one with the differential and sub for the other. I'll look at examples like that next time. We will talk about both of the powers being odd, both of the powers being even, and then we'll talk about the secant and tangent integrals. So you have what you need to go ahead and get started. Please wrap up the homework from last week with those looping integrals if you have not already done so. I want to say that there will be a looping integral on the test, right? Your first exam is not all that far away. We're getting pretty close to the first test. After we finish section 7.4, I will release the study guide for the first test. Exam 1 will cover all the way up through section 7.4. 7.5 is kind of a review section. So the test will probably be late next week or early the following week. It depends on how quickly we get through the rest of this material. But we're not that far off. Okay, so finish up the integration by parts homework, get started on the new homework. It's already out. We don't have everything we need to do all the stuff in the new homework, but you do have everything you need to get started. Any sine, cosine integrals where there is an odd power, you now have the skills to do. Next time we'll do the even powers, and then we will look at the secant tangent integrals. Is there anything you guys would like to ask before I end the meeting? Okay, then this is where I'll end it. I hope you guys have a lovely rest of your day. If you do need anything, I have an office hour starting at 1 o'clock, 1 to 2 p.m. Otherwise, I'll see y'all on Wednesday. Take care.